Look at a piece of glass shattering. In the physical world, this is a continuous event, infinite shards moving through continuous space. But a computer processor is blind to physical space. It only understands discrete arrays of numbers. To make a silicon chip comprehend the trajectory of flying glass, we need a mathematical translation layer to convert physical geometry into raw data. This diagram shows the solution: a vector. A vector is a mathematical quantity defined by exactly two properties: its magnitude, or length, and its direction. By assigning numerical values to these two properties, we encode spatial reality into an algebraic array that a processor can instantly compute. This specific translation is what makes modern computing possible. 3D modeling, game development, robotics, and machine learning all rely entirely on vectors to function. Mastering linear algebra is how we teach a calculator to simulate reality. Let's look at how a computer manipulates these spatial units. Here we have two distinct vectors, labeled A as A1, A2, and B as B1, B2, plotted on a 2D plane. If we want to compound these spatial translations, we add them together. Geometrically, this means placing the vectors tip to tail to form a new continuous path. Mathematically, we add their individual coordinates. If vector A is 2, 3, and vector B is 1, 4, adding them together lands us exactly at the new coordinate of 3, 7. Conversely, vector subtraction calculates the direct path between two endpoints. We can also apply scalar multiplication. Multiplying a vector by a scalar k alters its magnitude, or length, while keeping its exact angle permanently locked. When a physics engine calculates where an object should move in the next frame, it is executing rapid, continuous vector addition. And when you press the gas pedal in a racing game, the system uses scalar multiplication to lengthen the velocity vector, calculating precise acceleration. Basic vector arithmetic is the foundational logic computers use to calculate discrete, frame-by-frame motion. Beyond calculating movement, vectors let us precisely measure space. Here is an isolated vector A with coordinates 3, 4. We calculate its magnitude, or absolute length, using the Pythagorean theorem. Treating the coordinates as sides of a right triangle, the hypotenuse is exactly 5. We can expand this logic to measure the absolute distance between any two distinct coordinate points. This diagram maps 2 points at 1, 2, and 4, 6. Using the distance formula, we subtract the corresponding coordinates, square the results, and take the square root to find a geometric distance of 5. In computer graphics, calculating this distance determines whether two objects are close enough to trigger a rendering boundary or a collision event. But this exact same mathematical formula is equally critical for non-visual operations in machine learning. Machine learning models use feature scaling to normalize independent variables. Feature scaling is a method used to standardize the range of data points so they can be compared evenly. The distance formula dictates exactly how far apart two of these data points are within an abstract multidimensional feature space. These magnitude and distance formulas give the computer a universal metric to evaluate precise proximity, whether measuring physical objects in games or analyzing abstract data in AI. Next, we can multiply vectors together to extract specific geometric relationships. Look at this calculation for the dot product. Multiplying vector A and vector B outputs a scalar, a single number like 14, rather than a new vector. Geometrically, the dot product calculates how much one vector projects onto another. This makes the dot product a precise mathematical measure of directional similarity. Machine learning algorithms rely on this calculation to compare high-dimensional arrays. By calculating the dot product between a user's past behavior and a database of products, an ML system determines overlapping preferences and generates a recommendation. This same similarity measurement drives lighting calculations in computer graphics. This simulation relies on the Phong lighting model, an algorithm that calculates illumination by combining ambient, diffuse, and specular light reflections. To do this accurately, it uses the dot product to calculate the angle of incidence between the light and the surface. The computer checks the parallel alignment between a light ray vector and a surface vector. The higher the dot product, the more direct the light, and the brighter that specific pixel is rendered. The dot product is the indispensable tool for measuring alignment. It is equally crucial for tracing a ray of light and grouping user behavior. This diagram demonstrates the second method of vector multiplication, the cross product. Notice how the vectors A and B lie flat on a 2D grid. The formula for the cross product takes the magnitude of A times the magnitude of B times the sine of the angle between them, multiplied by unit vector n. Unlike the dot product, it outputs a new 3D vector instead of a single scalar. The core geometric property of this new vector is that it is perfectly orthogonal, meaning it sits at a 90-degree angle to both of the original vectors. Because it requires 3 dimensions to calculate, the cross product is heavily restricted to, and practically required for, 3D graphics and physics engines. It is used to calculate surface normals. A surface normal is a directional vector that points precisely outward from a flat plane. By generating this orthogonal vector, the cross product tells the computer exactly which direction a 3D polygon is facing. The cross product generates the orthogonal frameworks required to calculate realistic object collisions and complex geometry in any 3D simulation. We can now synthesize these individual operations into a complete evaluative system. Here we have 2 arbitrary vectors floating in 3D space, separated by an unknown angle, theta. To find that exact angle, we combine the dot product and magnitude calculations. This equation divides the dot product of the vectors by the product of their magnitudes, locking an abstract spatial angle into a concrete numerical value. Extracting this exact angle is the mechanism that allows an AI clustering algorithm to accurately group massive sets of data, and that exact same formula is simultaneously responsible for determining how a bullet ricochets off a piece of armor in a physics engine. Processors remain blind calculators operating within a continuous physical universe. Studying vector mathematics provides the core vocabulary needed to communicate with those processors. Linear algebra is the programming language of space, translating discrete numbers into the architecture of modern computing.